Hi everyone, it's me again. So today I'm streaming. You're not expected to watch it live, but I thought I would just do it this way, just for the sake of continuity. And our subject today is going to be algorithms. So we're going to go back and review a little bit from yesterday, although not too much, because we did use some time on Monday to talk about kind of the future of the class going forward. So today we're going to move right into algorithms, and we'll start to talk about algorithm analysis. Then towards the end of class, we'll introduce a data structure that you're going to be working with on the next few homework problems. It's called a list. Lists are also coming up in the MP. This is kind of a nice convergence of a couple of things that we're talking about together at the same point in the class. So on Monday, we talked about the fact that an algorithm is a series of steps that you take in order to solve a problem. And we think about algorithms particularly in terms of how they're implemented by computers. That's what we're working with. The way that we implement algorithms as a computer scientist is really by using these building blocks that we are now capable of using in our programs, right? So the ideas that we've been introducing, that you've been introduced to in the beginning of the class for how to structure your programs and the types of things that computers are good at, are really the building blocks of the algorithms that we're going to work on together. They'll get more complicated, but they're really based on these basic building blocks, right? So in order to implement an algorithm on a computer, we utilize its capabilities to perform simple calculations like math, save results into variables, make simple decisions about what to do using conditional statements, and repeat these steps multiple times using things like loops. And so we'll see in a minute when we go back and kind of redo GCD how each one of these comes into the picture. We're also, for the rest of the semester, going to be talking about data structures. So a data structure is a way of structuring data. It brings different data values into a particular relationship with each other. Frequently, this involves adding some type of metadata. So you start with the data, and then, for example, in an array, we actually put data into an order. We took a bunch of data values and we put them into an order. So afterwards, there's structure. There's a next value for certain data values at a previous value. And there's also metadata, right? There's an index within that array. And we talked about even just putting data into an array already allows us to do cool things like manipulate computer audio, right? Or even video. As programmers, we utilize some of the techniques and some of the new ideas that we talked about in the object-oriented portion of the class in order to implement data structures. So we do this using a mix of primitive types, which allows us to store one value, objects which allow us to join multiple values together. We can use, and we will use, existing data structures like arrays to build more complicated data structures on top of, and also references. So this idea that we talked about before break of using object references as a way to kind of link one value to another, particularly when we look at lists. So lists are such a cool data structure to work with, as you're finding out in the MP. It's also a really neat data structure to implement, because the two different implementations, one is going to use an array. That's going to lead to one set of performance trade-offs. And another one's actually going to use links, references to link different data values together. That's going to produce a different set of performance trade-offs, right? And we'll get into that as we talk more about lists. These two subjects are highly complementary. So data structures typically exist, and again, we'll talk about this when we talk about lists. Different ways of structuring data exist because certain algorithms then utilize that structure in order to operate more efficiently. So technically, you could store all the data that you ever wanted to use in an array, but there are certain algorithms that run very slowly on data stored in an array that can run much more quickly on data if it's stored in a different way. And so we're going to implement algorithms that utilize specific features of data structures, and we're also frequently going to implement data structures with a certain algorithm in mind, right? We have something that we want to do with the data, right? And this is also a great chance for us to practice all of these imperative and object-oriented programming skills that we've built up till this point in the class. So again, this is really my favorite point in the class because, we've taught you kind of all the dry and boring stuff on some level, all the basics, sort of simple object-oriented stuff, and now we get to dive into, or at least, dip our toe in the water of the real conceptual concerns of computer science as a field and some of the more interesting things that computer science think about and implement. And of course, we have a couple of new ideas that we'll introduce along the way, specifically today and over the next few classes, this idea of being able to talk with a certain degree of accuracy about how long a particular algorithm takes to solve a problem. As a computer scientist, one of the nice things about, the way that we think about algorithms is by the time you have become so specific about how to solve a problem that a computer can actually take that specification and solve the problem, you actually are in a position now to analyze that solution and determine how long it's going to take to solve different types of problems, right? And the amount of time it takes, or sometimes the amount of computer memory it takes, or other factors, are big trade-offs that we make when we choose one algorithm over another, right? This can be the difference between an algorithm taking weeks to finish a job and that algorithm being able to finish the same job in a second, right? And of course, that makes a huge difference in terms of the way that we solve problems in the world. All right, so on Monday, we introduced this idea of a particular problem that we're going to develop an algorithm for. So we have two numbers, and we want to determine the largest number that divides both of them evenly. This is called the greatest common divisor, or greatest common denominator of these two numbers. We can actually extend this to handle any number of integers, but for now, we're just going to handle two, okay? There are complicated ways to solve this problem. There are multiple different algorithms for calculating the GCD. And if you were in a position where you had to do this and performance was very important, you would go and you would implement, or you would find an implementation of a much more sophisticated algorithm. But what we talked about on Monday was this idea of using a simpler approach, something that's sometimes known as a brute force solution. So a brute force solution is a category of algorithms that solve problems in a very, very simplistic way. So again, what's a brute? A brute is not particularly smart. A brute wouldn't be able to implement this very sort of sophisticated algorithm to compute the GCD. Instead, a brute is going to rely on just its brute strength, right? And in this case, the computer's brute strength, the computer's just brute speed and its ability to do these repetitive tasks over and over again, right? Computers aren't smart, right? They're just fast and they're very good at doing simple things, right? If we program them effectively, they can seem very smart, right? But at the core, they're performing very, very simple operations, right? One of the reasons that we sometimes want to implement or think about brute force solutions is we want to compare their performance with the performance of a much more sophisticated algorithm that solves the same problem, right? If a simple algorithm can solve the problem well, at least maybe for the particular types of the problem that we need to work on, the sophisticated algorithm may not be necessary, right? Or the simple algorithm, the brute force solution, will allow us to appreciate how incredible and how fast the sophisticated solution is. There are certain problems where the brute force solution is terrible, right? It takes way, way, way longer. You implement this much more sophisticated algorithm and suddenly it's super fast, right? And so you see this huge speed up and you feel like this is computer science as a field. This is the conceptual core of what we do. All right, so, and again, one of the reasons that we can get away with these brute force solutions is that computers are so fast, right? And so sometimes it makes sense to try the simple thing first, again, either as a point of comparison or depending on the kinds of problems you have to solve, you might never need to do something more sophisticated. All right, so last time first we had decided that we needed to satisfy the check-style gods by renaming this function to use lowercase. And then we had, and then we had gone ahead and implemented our GCD, and we had done this in a very basic way. So I'm just going to reprise the solution from last time. We created a function called GCD that took two numbers. So essentially, the two observations that we made were that the largest number that can be the GCD is the smaller of the two numbers, and 1 is always a GCD, right? Sorry, 1 is always the denominator of everything, right? And so if we want to find the GCD, our brute force algorithm is going to be start at the smaller of the two numbers. Try that number and see if it divides both evenly. If that does, then it's the GCD. Otherwise, try a number that's 1 smaller, and keep doing that until we get to 1. Because once we get to 1, we know that we found a solution, okay? So the first thing we need to do is we need to calculate the minimum, and we'll do that by saying, first we say the minimum is the first. If the second is less than the first, we say minimum is equal to second. And then we write a loop, okay? So our loop is going to go through the numbers. We'll call this candidate. We're going to start at the minimum. We're going to stop when we get to 1. Okay, so we're going to continue the loop as long as candidate is greater than 1. And in each iteration, we're going to try a number that's slightly smaller. I'm looking for the greatest common denominator. If we wrote this loop the other way, we would always stop with a small number, but we want a big number, right? We want the number that's the largest. So again, brute force solution, we are going one by one, and we're testing these numbers. And the way that we test the number is we say, if candidate divides first, so we're going to use this remainder number in Java that returns the remainder when you divide first by candidate. And if candidate divides second, then we have found our number. Otherwise, we continue. Down here, if we get all the way to the bottom and break out of the loop, it means that there's no number that divides the two evenly that's larger than 1. And so 1 is actually the GCD of the two numbers. Okay, so, oops, got a typo right here. So now it's mad about something else. Oh, I need to finish my conditional here. It's sloppy. All right, and so if you actually test this using another program, this is actually correct. Okay, but I want to point out, how do we implement this algorithm, right? So our implementation is here, right? But the algorithm, the way you would describe the algorithm is you'd say, start with the smaller of the two numbers. So that's what we did here, and we used the fact that computers can store data and make simple decisions. So we have to decide which of the numbers is smaller. Then, see if that's the GCD, and the way we did that was by testing it, right? We tested it to see if the remainder, when I divided the first number by that number, and when I divided the second number by the number, was 0. If that's true, then I found the GCD. Otherwise, try the next smaller number. And I continue that until I get to 1, because I know that 1, if all else fails, 1 will divide both of the numbers. And there are numbers that don't have any common factors that are known as relatively prime to each other, right? And so in this case, these two numbers down here, despite the fact they're not prime, right? This is not a prime number, it's even. But they're relatively prime because they don't share any common factors, right? The GCD of these two is 1. Okay, so I have a simple algorithm to solve this problem, and this algorithm will work, right? The question becomes, this is our brute force algorithm, right? So we basically we're applying a brute force solution. We try every number until we get to one that works, right? Now, again, I want to be careful here about how I talk about this subject, because computers today are really fast. And so, it's a common, I think maybe too common among people that are getting started in computer science to get really obsessed about the performance of certain things that don't actually matter, okay? Performance analysis is a complicated and sophisticated topic that even experts in the field will frequently get wrong, okay? So if you're, particularly when you're trying to solve another problem, it's a very valid approach to implement simple algorithms and use them as long as they're not a problem. Once they become a problem, once your whole system or your app or your program is slowing down because it has to do this calculation, and you're using an algorithm that's really unsophisticated, then you fix it, okay? But you don't fix it ahead of time, right? Let performance become a problem and then solve it at that point, okay? But at some point, someone is going to, particularly as a computer scientist, this is something that we think about and care about, right? How long do things take? Someone's going to ask you, someone's going to expect you to know, and someone's going to expect you to have thought about this. And this is one of the conceptual concerns of computer science, right? This can also start to matter in practice for a variety of reasons. So an algorithm for doing search that runs fine on a small number of documents may not run at all at Google on trillions of documents. Right? So at some point you may have this massive problem that you can't solve. You're trying to search the whole human genome or something like that, right? There is big data out there in the world, and bad algorithms frequently perform extremely poorly on big data. Another problem might be certain things just start to get slow, right? Slower than you are comfortable with them being, right? This has happened to me a few times. You may end up in a position where your company is paying for computation. So you're renting computation from a cloud service provider like Amazon or Google or whatever. And so at some point, the slowness of your algorithm is starting to translate into actual dollars and cents, right? You are paying more, you might be paying through the nose for all of this compute that you're using because you're doing things in an unsophisticated way, right? This is sort of a variant of the fact that the incredibly fast computer is slow. Or, you're in a job interview and someone's actually asking you to solve a problem and to explain why your solution performs a particular way, right? So it's worth thinking about this, it's worth understanding it, and it's worth being able to talk about algorithm analysis in a precise way. So we're going to introduce some terminology today in order to allow us to do that. So let's start by talking about this brute force GCD algorithm, right? And what we want to do is we want to think about, first of all, let's think about some special cases, right? So let's say I give it the GCD of 4 and 6, right? So I'm going to go back here and we're going to look at our implementation of this, okay? And actually, you know what we can do? Let's actually try to measure this on some level, right? So here's what I'm going to do. I'm going to create a static variable count. And what I'm going to do is that when I start running my GCD algorithm, I'm going to set count is equal to 0. And then what I'm going to do is I'm going to count kind of the number of times I have to execute this loop, okay? So every time I go through the loop, I'm going to bump the count. This won't change the operation of my algorithm, but what will allow me to do is after I run it, it'll allow me to, and again, this is one of the maybe few cases where I'm actually going to use a static variable, right? This actually give me a chance to test out how long it takes that algorithm to run, right? So here, the GCD was, let me comment out these other calls to GCD. So on line 20, the GCD of 10 and 8 was 2. My loop ran 7 times, right? And so why did it run 7 times? Well, I started with 8, and then I tried, the numbers I had to try were 8, 7, 6, 5, 4, 3, 2, right? I ran 7 times. I got to 2, I was done, right? So let's try 4 and 6. 6 and 4, now this takes 3 times, right? Because I start at 4, which is the smaller of the two numbers, and I try 4, 3, 2. I found 2, 2 is the GCD, I'm done, okay? So for that problem, it takes 2 times. What about these two numbers, right? So again, it kind of depends on what the GCD actually is, right? Let's try it though. Let's try 185 and 2045. Back here, 185, 2045. It looks like my loop ran 181 times, okay? The GCD of those two numbers is 5. So I tried 185, 184, 183, blah, 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 blah. I got all the way down to 5 before I finished, right? And the truth is, if I use really large numbers here, right? Particularly if I can find some numbers that are relatively prime, and I'm not sure these two are relatively prime, right? They are, it turns out, right? Then I can, this program may end up running a long time, okay? So now you're seeing the program's timing out. It's taking too long to finish because I'm using numbers that are too big, and this algorithm is really dumb, okay? So if you used a more sophisticated algorithm, you'd be able to solve this problem without it timing out, right? But I'm getting to the point where this problem is taking too long. But let's go back to thinking about how long it takes. So what we were able to do is we were able to talk about how long it took in the general case, in specific cases. So we talked about 4 and 6, well, it takes 3 iterations. 185 and 2045 takes 181 iterations. But what about if I give you two numbers, m and n? I'm not going to tell you what the GCD is, but I want you to estimate how long it could take, right? Here's how you would do this. You would say, okay, well, I don't know what let's perform a worst case scenario. Okay? So the worst case scenario is the GCD is 1, right? So I have to start at the minimum of m and n, and I have to try every number all the way to 1. So that loop is going to execute the minimum of m and n times, whichever is small. The best case scenario is that the GCD is m or n. right? The smaller of the two, in which case the loop executes once, right? So again, if I go back and let's try another instance of this. So let's do something like, let's imagine the two numbers are, well, let me try something like this. Let's try one number, and let's try another number that divides that number evenly. These are both really big, but you'll see now it only took one iteration because the smaller of the two numbers was a multiple, right? The larger was a multiple of the smaller number, so the smaller number is the GCD, right? So this example is illuminating some of the features that we're going to talk about when we talk about algorithm analysis in general, right? Specifically, this idea that we need to be able to talk about how long an algorithm will take without understanding much about its inputs. It also exposes the fact that sometimes the same algorithm can run really fast in certain cases and really slow in other cases. We sometimes call that the best case scenario. The algorithm runs really fast. In this case, if the GCD is one of the two numbers that I'm trying, and really slow, which in our brute force algorithm is the case where the two numbers are relatively prime. So they don't have any common factors, and the GCD is 1, because I have to start at the minimum of the two and work all the way down, right? Okay. So what we've been doing is a form of something that's called algorithm analysis, and that's going to be the topic for our next few classes. And this is something that you will continue to think about throughout your career in computer science. If you go on and take other courses in our department, if you go on to take, like 173, 225, 374, like you're going to continue to think about and learn about this particular topic, right? It's going to happen. So this is just a preview, and the way that we talk about it in 125, I want to be very clear, is simple, right? We're starting with a simple formulation of algorithm analysis that's designed to give you kind of an intuitive introduction to this topic. Once you get to 173 and 225 and 374, you will become much more specific. You will prove things about algorithms, right? We're not going to prove anything in this class, right? Instead, what we're going to do is we're going to observe, we're going to measure, we're going to talk about categories, and we're going to think about big picture, right? Again, you will go on and you become much more specific and much more sophisticated in terms of how you do this. But what I'm trying to do is give you a broad overview that can serve as a conceptual framework that will help you in later courses. Okay? So essentially, when we analyze an algorithm, we want to know a couple things about it, right? We might want to know how long it takes, right? But we might want to know other things about how many computer resources it needs, like how much space does it take up, right? How much memory is required for the algorithm to run, right? And so there's multiple different types of resources that we might want to think about. Normally in this class, we're going to focus on time, but there's a few places where we're also going to talk about memory because there's trade-offs sometimes between the two. Lists are a good example of this. So when we analyze algorithms, we typically want to analyze them for the general case. We want to talk about in general, right? We don't care about a specific set of inputs because when we implement an algorithm, we need it to work for all of its possible inputs, right? So our GCD algorithm that we just implemented, the brute force GCD algorithm, will work for all possible inputs. It's not a good algorithm, right? But it will work for all the inputs you give it. It might take a long time in certain cases. We saw that. We already saw it start to time out on certain values. But it is correct in the sense that we'll always find the answer if you give it long enough, right? But when we talk about the performance of an algorithm like that, we want to talk about its performance in the general case. We rarely care about how long it takes to solve one specific problem. So, what's the performance of our GCD algorithm for these two numbers? We don't care about that. We care about given two numbers m and n, where m and n could be any number, right? Tell me how long it's going to take in that case, right? We also frequently think about how long these algorithms take on very, very large inputs, right? This is sort of known as analyzing the limiting behavior of an algorithm, right? So when the inputs get really, really big. Part of the reason for that is that it simplifies the analysis because it causes us to focus on certain components of the algorithm, right? I'll go back and look at GCD in a minute and I'll talk about this, right? We also frequently want to think about what are the best case runtime, the worst case runtime, and then hopefully we can think about maybe what an average case is. But average case turns out to be much more difficult to think about. Best case means, if the inputs have certain properties that cause the algorithm to behave extremely well. Worst case means if the inputs have certain properties that cause it to behave extremely poorly. We already saw that with GCD. The best case was the smaller number is the GCD. It divides the larger number. And I'm done. The loop doesn't execute at all, right? Worst case is the two numbers don't have any common factors. And so the GCD is 1. So I have to start at the smaller number and work all my way down, and that takes a while, right? And essentially what we're trying to figure out is how does the algorithm's performance depend on its inputs, right? So let's go back and look at GCD again, at our GCD algorithm, right? And so one of the reasons that we typically want to think about big numbers is because if you think about how long this algorithm takes to run. So let's look at the code. So there's a little bit of time that we need to spend up here figuring out what the minimum of the two numbers is, okay? But then I get into this loop. And this loop is really what's going to dominate the performance of this algorithm, particularly when the numbers are big. Because when the numbers are big, it's going to take me a couple of steps to calculate the minimum here, right? I have to do that for every pair of inputs, and it takes the same amount of time, roughly. But then I get into this loop, and this loop depends on the size of the minimum, right? It depends on the size of the smaller of the two numbers. And so if I do 4 and 6, this loop only executed a couple times. If I do massive numbers, almost all of the time that this algorithm spends executing, it's going to spend executing in this loop, okay? And so this loop becomes the dominating feature. And so that's one of the reasons we usually think about what happens is the numbers or the inputs to our algorithm get very big, because that allows us to ignore things like calculating the minimum, right? And some other steps that the algorithm might take that are really constant time. They don't depend on the inputs, right? For our GCD algorithm, the part of the performance that depends on the inputs is this loop, because this loop runs at most the number of times of the minimum of the two numbers. Okay, good. All right, so we talked about this, great. Okay, so now let me introduce this notation that we use. This is sometimes known as big O notation. And again, you guys will go on and you'll see this in a much more rigorous mathematical setting. What we do with big O in CS125 is we use it to establish categories, right? Those categories differentiate the general behavior of different algorithms from each other in a way that we're going to see in a few minutes, okay? And the way that we put an algorithm into one of these categories is we think about what happens when its inputs get really big, okay? So there are two components of big O analysis, right? One of them is determining what category the algorithm is in. The other one is figuring out what constitutes what's the feature that constitutes the algorithm's performance, right? So we'll talk about both. These are the complexity categories that we're going to be working with in this class, right? And we actually won't even work with all of these, right? But I just wanted to show these to you because this hopefully gives you some sense of what's at stake here, okay? Because the differences in performance between these complexity categories is actually incredibly huge between certain ones, okay? So what is this graph showing? So over here, the labels here are sort of unimportant. So essentially, on the x-axis, you can think of this as the size of the problem. And on the y-axis, what we have is the amount of time that it takes for the algorithm to run. And what you'll see here is that depending on the class that the algorithm is in, some algorithms, as the problems get big, their performance, they get only a little bit slower. Down here, the ones that are close to the axis. There's a couple of very, very good complexity categories here that are extremely desirable, right? On the other extreme, there are some algorithms, some classes or categories of algorithms, that as the problem gets big, their performance gets terrible, right? So over here, this is O(n) factorial. So algorithms that are O(n) factorial take a number of steps equal to or roughly equal to n factorial, where n is the size of the input. This line is like, a rocket taking off. It's going straight up, okay? So you imagine if you work somewhere or if you're trying to solve a problem and it only gets a little bit bigger, an algorithm that requires n factorial is getting so slow that it's just completely impractical. We'll actually talk when we get to sorting about an amusing sorting algorithm turns out to be n factorial, but in general, it's just for the sake of a laugh, right? In general, n factorial algorithms are terrible. Like, you can't implement them you can implement them, but you can't use them most of the time because their performance is so slow. It gets so bad so quickly that even a small problem becomes quickly intractable, right? So frequently what happens when we talk about good algorithms or bad algorithms is we're talking about what category is the algorithm in, right? So for example, a clever algorithm might be a problem for which the brute force solution is O(n) squared, but there is an O(n) log n algorithm, right? So the O(n) squared algorithm takes this much time as the problem is getting bigger. If I can move that algorithm into O(n) log n, look at the difference here. Even for a medium-sized problem, there's this massive performance difference. Same thing if I can take a problem that's O(n) log n and make it O(n), or linear time, right? Look at over here, huge performance difference, right? So again, our conversation about this topic is really going to be guided by these categories, right? We're going to talk about, okay, well, that algorithm is O(n), right? But there is an O log n algorithm for that problem, which is down here, right? Or, sorting algorithm is n log n, but it turns out that in simple cases it might be O(n), right? Okay, so let's delve into these categories a little bit more, and we'll also look at some examples, right? So what I want to do is I want to start building your intuition in terms of things in your programs that might actually map into some of these complexity categories. Okay, so we're going to start with the simplest one. This is O(1), or O constant, right? This is a constant time. Algorithms that are constant time have no dependence on the size of the input or anything about the problem. It always takes the same amount of time, okay? This is great, right? But most algorithms aren't constant time. However, various operations that you might have in your program are constant time. So for example, retrieving a value from an array, like I'm doing right here on line 2, this is a constant time operation, right? Roughly, once you guys get into 225, Carl's going to come back and, wash my mouth out with soap for saying that, because it turns out to be completely technically true, but whatever, right? For our purposes, it's correct, okay? All right, but so again, most algorithms are constant time because they do need to solve the problem, and if the problem gets bigger, they need to do more work, right? But basic operations within your program, like assigning a certain value to a variable, is constant time, right? Okay, so this is a much more useful complexity category. This is called O(n), right? O(n) means that if the problem is size n, then the algorithm takes n steps, or roughly n steps, okay? And we're going to talk about quite a few algorithms, and quite a few algorithms that you guys have already seen are O(n), okay? And O(n)'s not that bad, right? And there are certain algorithms for which O(n) is clearly the best that you can do, right? So for example, anything that involves a single loop through an array. So let's say I have an array of numbers here and I'm computing the sum. The sum is O(n), right? And let's think about why that is. If the algorithm has n elements in it, and I want to compute the sum, in order to do that, I have to add every element. So I have to read every element out of the array one at a time, okay? There's no other way to do it, right? You can't come and tell me, well, I have a constant time algorithm for doing the sum, because I was like, how does that work, right? You have to see every element in the array in order to add it into our sum, right? So frequently, when we see an O(n) algorithm, we see a single loop, right? So here's an example. This is a single loop that goes through an array. In this case, the algorithm is O(n), where n is the size of the array. If we go back and look again at our GCD algorithm, this is another case where what we see is a single array. And this GCD algorithm is also O(n), where n is the smaller of first and second. right? So ON algorithms are pretty common, and we will talk about many of them as we go along. All right, so this is ON, right? Now let's talk about a slightly more interesting ON algorithm, right? So let's say we're doing a search. We're looking through an array for a particular value, right? So here I have an array of integers. I have a simple for loop that's using our enhanced for loop syntax that's going through pulling values out one at a time. But here's the rub. When it gets to the value that it was searching for, which is looking for, which isn't declared here, it stops. So what about this algorithm? So this algorithm is always going to take ON. The best case performance is ON. The worst case performance is ON. It always goes through the entire array. This algorithm is a little bit more interesting because if it finds the value right away, it stops immediately. If it goes all the way to the end of the array and doesn't find the value, then it might take longer, right? So here's an example where we need to think about the best case and the worst case. So we'll get some practice doing that. Best case here is it's the first value in the array. So I immediately find the value I'm looking for. In that case, the algorithm takes only one step because it breaks as soon as it sees the first value in the array. The worst case is that the array doesn't contain the value I'm looking for, because in that case I'm going to go all the way through front to back and never find it. And also if it's the last element, right? So either if it doesn't contain the item I'm looking for, or if it's the last element. The average, so let's say that, on average, let's say that the array always contains the value somewhere, then in that case the average is ON squared. ON over 2. Now in our class, we are not going to worry about constant factors inside of our big O categories. O of 2n, we're going to say is O of n. O of n over 2, we're going to say is O of n, right? We're just putting things in categories. We're not worrying about those multipliers inside our big O notation, right? So an algorithm that takes, if the size of the problem is n and it takes n over 2 steps, we're going to call that an ON algorithm. Now in practice, if you went to Google and you came up with a way to take their search algorithm and make it twice as fast, you would probably get a big raise, right? So in reality, people worry about these factors within the big O notation. So Google's search algorithm might be O log n, and you might make it O log n over 2, and you might get, again, like a big promotion because of that, right? So out there in the real world, people actually do care about making things twice as fast, 3 times as fast, right? In this class, we're just going to think about categories, right? So we're going to be happy if we can take an ON algorithm and convert it to O log n, right? Or an n squared algorithm, make it ON. Okay, so now let's look at ON squared. So this is the next type of problem. And this problem means that if the input has size 4, then it takes 16 steps to solve the problem. If the input has size 10, it takes 100 steps. If the input has size 20, it takes 400 steps. So it's growing exponentially with the size of the input. One place where you might see this is if you see a nested loop. Okay, so here's an example, and this example is actually doing something really dumb. This is a bad algorithm. So I'm passing in an array. It's going through the array, but it's actually, I have an outer loop that's indexed by I and an inner loop that's indexed by J. I'll leave it as an exercise to the reader what exactly this loop is doing, right? What this algorithm is doing, right? But this is a poor algorithm for solving this problem. There's a much faster algorithm to do it. But this algorithm will take ON squared steps, right? Because what's happening is every time I run my outer loop, I'm running my inner loop about n times. It's not exactly n because I'm starting at I, but you can estimate it as n. So this runs n times, this runs n times. And so every time I run the outer loop, I have to run the inner loop n times. So that means that by the time I'm done, I have worked my way through this part n squared times, okay? And one of the ways that you can identify an n squared algorithm is through nested loops, right? There are other ways to implement n squared algorithms, but this is one of the telltale signs, right? So here again, like what am I actually doing if I think about best case and worst case? I do have a return statement inside my loop. And so it's possible that I get to the return statement right away, right? In that case, the algorithm well, I'm sort of giving away what the solution is. So essentially, this is an algorithm that's determining whether or not an array is sorted or not, right? And it's doing that by making sure that for every element in the array, all the elements that have bigger indices are larger, right? So it's looking for an element that's further in the array that's smaller than the current element. If it finds one, then the array is not sorted and it's going to return false, right? Again, this is a dumb way to check if the array is sorted. There's an ON algorithm to solve the same problem, right? But the best case is that I get inside this loop and I immediately find an element that's out of place, right? The worst case is the array is actually sorted and I have to go through all of the elements, all of these calculations before I realize that, right? The average case here is going to be ON squared, right? Because on average, the outer loop is going to run n over 2 times, and the inner loop runs n times each time the outer loop runs, and so this works out to like n squared over 2, but again, we're going to ignore the constant factor there. All right. And so again, so what we were looking at right here is an n squared algorithm, right? And you can see that n squared algorithms grow faster than linear, right? This is my ON algorithm down here, right? An n squared algorithm is growing quite a bit more quickly, and this is a problem, right? Because again, this is a dumb algorithm. There is an ON solution for this algorithm. So if you implemented that, you would end up moving this, improving the performance dramatically, right? Because you take something that's up here and you drop it all the way to down here. And that's a difference that you will notice, right? We will come back and talk about these logarithmic complexity categories, right? There's one where the runtime grows as the logarithm of the size of the problem, and there's another important category where the runtime grows as n times the logarithm of the size of the problem, n. These complexity categories result from features of problems that we haven't seen yet, but we're going to soon. When we get to recursion, these complexity categories become more common, right? We'll talk about them at that point, right? But in general, if your algorithm is able to make the problem half, like cut the problem in half each time, then you end up with something that's O log n, right? And again, recursive algorithms frequently have this property. We'll talk about that in a little bit. So, this is just an introduction to these complexity classes, but I do want to be, explicit about this, which is that, dumb algorithms, right? If you end up implementing a dumb algorithm for a problem, you bring it up in the category, right? So essentially, you might take a problem that really can be solved using an ON algorithm and implement an ON squared solution. And you just saw an example of that because our test to see whether or not an array is sorted is dumb. The problem is actually solvable quite easily, actually, in ON. But we implemented an ON squared algorithm, right? And so we're sacrificing a lot of performance because we were dumb, right? In contrast, a smart algorithm takes a problem down the runtime categorization, right? So for example, the GCD method that we implemented, our brute force GCD, is ON. But Euclid's method, which is a clever GCD algorithm, is O log n. It actually moves the problem down, right? It takes our solution, which is dumb. We know it works, but it's dumb. It's a brute force solution. And improves it by actually moving it into a completely different category, right? That is a huge, huge improvement, right? So, again, smart algorithm, we took an ON problem and we put it down into O log n. And O log n grows really nicely. It's way down here along the axis. So this was our GCD algorithm, the Euclid GCD algorithm, right? Dumb algorithm, smart algorithm. Same thing with testing whether a list is sorted, right? Our basic algorithm is ON, our dumb algorithm is ON squared, right? So our dumb algorithm has moved the problem up into a higher, slower complexity class. So I want to take a minute here to just, because this is the point in the class where, again, we're starting to talk about some of the deep conceptual concerns of computer science. And so I don't want to miss a chance to call out this problem, right? So, every field has its big unsolved problems, right? Math has many of them, right? frequently every couple of years you hear in the news about, well, maybe it's not every couple of years, maybe every decade. I've been alive for a couple of these discoveries now, right? Andrew Wiles with Fermat's last theorem. I can't remember the guy who recently solved this big unsolved problem in number theory. But there are these mathematical problems that periodically you read about in the news because someone has solved them. And in computer science, we have a very, very deep problem that's at the root of the field that remains unsolved, right? It's extremely interesting. Some of you might have heard about this already, and this is the question of, does P equal NP? And again, we do not have the requisite level of mathematical maturity in this class in order to really discuss this problem rigorously. But essentially, at its core, what it has to do with is, are some problems just fundamentally harder than other problems? So right now in computer science, we have a category. P and NP are these categories of problems, right? We have a category called NP, is non-polynomial time, right? These are problems for which we do not have a polynomial time solution. And there's only a small number of these, right? And they also seem to be related to each other, right? So they have structural similarities. So there's actually, I think, some evidence that if you have one of those problems, you can convert it to another one in the same category. So any NP problem can be mapped onto a different NP problem, right? The traveling salesman problem is a famous example of a problem that remains in NP, okay? There's also problems related to certain graph operations. So these are problems that are fundamentally very, very hard to solve. And then everything else is in this other category, right? Which is P, right? Polynomial time problems. So the question is, is there this category of problems that is fundamentally more difficult to solve than others, or are all the problems in P, right? So far we haven't been able to prove this, right? It seems as time has gone by and people have not found polynomial time algorithms to solve some of these problems that are in P. Essentially, I think people are becoming more confident that there really is this special category of problem that is really hard to solve, right? But nobody's been able to prove that yet. When somebody proves this, you will read about it on the news. It's a huge and extremely important problem in computer science, and it also has a lot of implications in other parts of mathematics. There's also like big prizes that are available for this thing, like $1 million that people solve it and stuff like that. So it's a very interesting open problem. And this is actually connected to Sudoku, right? Because it turns out that Sudoku, if you make the board large enough, turns out to be a problem that's in NP, right? And actually, one of the things that's interesting about this, right, I just want to point this out, because you might say, well, there's lots of problems that are in NP because I can come up with these problems that are like impossible to solve, right? But the trick is, the problems in NP have this nice property, which is that you can verify the solution very quickly. So if somebody solves the problem and gives you a solution, you can verify that it's correct in polynomial time. So let's think about Sudoku as an example of this. If I give you a Sudoku puzzle that's all filled out, you can verify that the solution is correct. You just check, there's a very simple algorithm for checking it, right? So I can check the problem in ON, where n is well, if the board is n, then it's ON squared, right? So basically in polynomial time, I can check whether or not your solution is correct. The question is, can you solve the problem, right? If I give you a board and you have to, with the numbers and you have to fill in the remainders, right? I don't play Sudoku, but I guess that's how it works. Can you actually complete the problem in a polynomial time number of steps? And so far, we don't have an algorithm for doing it. All right, so before we, hold on a second, I'm just going to clarify something. So before we wrap up, I need to provide like a brief sort of annoying interlude about Java primitive wrappers, because this is going to come up when we start working with lists. And you guys might be encountering this already on EMP. So in Java, there's the data structures that we're going to start building frequently will only store objects, right? And this is partly because object provides hash code and it provides equals and it provides these methods, right? So the question becomes, let's say I have a Java list and I want to stick an int into it. How do I do that? Ints, longs, things that are not objects that are primitive types. How do I insert them into these data structures that only store objects. And so the idea is that there's this thing called a boxing type in Java, right? The boxing types take a primitive type and they wrap it in an object. And the object can be cast back to the primitive type and vice versa, right? So here's an example. There's an object type called integer, capital integer. I can create one using this syntax. I also think I can create it just using an integer literal. We'll try that in a second. And I can cast, I can cast primitives to this if I want to, and I can cast things back, right? So this is a object that basically wraps a primitive type, right? And there's one of these for like every single type of primitive, every one of the 8 primitive types in Java. The naming convention is usually the name of the type capitalized. There's a couple of cases, char and int, where we finish the job, integer, character, right? Not super exciting, just something you need to know for the list stuff, right? So before I wrap up today, I want to introduce the data structures. We'll continue talking about algorithm analysis and data structures on Friday together, but I want to talk about lists because on the next few homework problems, you're going to start building this general data structure called a list. And we're going to implement this data structure several times because we're going to use this as a chance to not only strengthen your ability to work with object references, but also give you a chance to do some algorithm analysis, okay? So lists are, on some level, a generalization of an array, right? So remember, Java arrays were great. They put things in order, but they have this irritating limitation, which is that we can't change the size of them after we create it. So lists, in contrast, have these features that you might be familiar with if you use Python from Python that I can add. I can change the size as I go, right? So I have get and set operations that allow the list to work like an array. I can retrieve and set values by their indices. But I can also add and remove values. And what that does is it inserts then into the list, changing the size, right? So unlike an array where if I create an array of size 4, I can't change the size later. If I create a list of size 4, I can add things to the front, which will cause the list to grow in size, and I can also remove values, which will cause the list to shrink in size. Lists are one of these, one I refer to as the 2 data structures that you meet in heaven. They are incredibly useful between lists and maps, which is another data structure that you meet in heaven, which we'll talk about in a couple of weeks. You can actually get a long way doing a lot of general purpose computer science and problem solving just using those 2 data structures. So one of the reasons that we're implementing lists, and we're going to do this twice, right, is that it's going to give us a great chance to practice with data structure trade-offs, right? So the 2 lists that you implement are actually going to utilize the same interface. So from the perspective of, again, interfaces, here they are, from the perspective of the user of the interface, right, the list is going to behave identically. They're both going to support get and set. They're both going to support add and remove. But what we're going to see as we implement them is that we're going to implement 2 different types of lists that internally work very differently. One is going to store the values in an array, and the other is going to store the values by linking them together using object references. Both of them will support the same interface. So again, from the perspective of the user of the interface, they work identically, but they have very different performance trade-offs, right? We'll see that lists that stores items using arrays make certain things fast, right? So fast lookups. But when I want to modify the list, like add and remove elements, those operations are slow. In contrast, when we use linked lists, which we'll talk about more, don't worry, this is our other type of list. These are going to have slow lookups. So lookups are going to take on, but certain insertions are fast. So if I insert in certain places in the list, particularly at the front or at the back, then the insertions will be quite quick, right? And these will also prevent different memory usage. These will also present different memory usage trade-offs, right? Java actually has a list interface that is an official part of Java that is implemented by several other classes. We're going to use a simpler version of this. This one has a bunch of methods and stuff like that that I don't want you to have to implement. So here's our list interface. It has 5 methods. It has get and set. Get allows me to retrieve the value retrieve an object stored at a particular index. Set changes the value at a particular index. Add inserts an element into the list at a particular position, and removes an element from the list at a particular position and returns that element. And then finally, there's also a convenience size button. Okay, so that's it for today. We're going to pick up here on Friday. So on Friday again, we'll be live streaming at 10 a.m. normal class time. I have virtual office hours today from 4 to 5, so I'll be on Zoom. There's a link to the meeting room. This is not a great place to ask questions about the MP or the homework, because this will be kind of a meeting where everybody will be there, right? So I won't be able to really talk to you privately. I think I need to figure out a way to kind of set up private appointments. I have some ideas about how to do that, so I'll work on that today. But we will provide times for you to come in and talk to me privately if you need to. But if you just want to chat, or if you have questions about how the course is going or our transition to virtual instruction, please come by today, join me in my room and say hi. The other thing I want to announce is that, so we've been working furiously on a new system that we're going to try out to help us hold office hours, right? So this is essentially something that will allow the CAs to work with students that need help on the homework or on the MP in a way that we want to be as similar to what we do in office hours as possible, right? So the idea here is that you'll log on to this, you'll get set up, you'll share your screen, you'll be working, and then periodically a CA will arrive into your virtual room, be able to see your screen, be able to debug a little bit with you, offer some suggestions, and then be gone, right? And this will happen repeatedly, because as long as you're there, you'll be visited regularly by one of our course staff. So we're going to start, I think, experimenting with this today. It's new. I'm sure there are bugs. I'm sure it won't work perfectly for everybody. I hope it works for many of you. We'll definitely take feedback on this. We're going to spend some time kind of working out the problems and bugs. This was developed extremely quickly, and so I'm sure, I wrote it, I'm sure there's problems with it, but I think it's really going to help us, right? I think it's really going to help us do a better job of helping you guys with the assignments. All right, I hope the quiz went well. I'm also going to solicit feedback about today's quiz on the forum, so if you took it, you ran into some technical issues, please let me know. I'm working closely with the people that develop PrairieLearn to make sure that this works for you. They are planning to add some resources to their system, and hopefully by the time we get to the midterm next week, this will be a little bit smoother. It looks like things went okay today, but I'm happy to hear feedback about that. So, all right, I will be on Zoom, not Zoom. I'm not using the word Zoom. I'm not calling this Zoom. This isn't Zoom anyway. It's YouTube Live. I'll be back online with you on Friday. Good luck on MP3. Please get going on that. And I will be with you guys later.